Hi everyone. So today we're going to be taking a look at a reintroduction to microprocessors. We started off with the Atmega 328 and now we're going to move on to the PIC32. So we're going from an 8-bit architecture to a 32-bit architecture. So we're gradually increasing in complexity. So the slides that you're about to see were originally written by Mr. Lucio di Jasio. He's a fantastic author on microprocessors and microcontrollers. I absolutely recommend his books. There's a link to his PIC32 book in the YorkU library. Now, this set of, this part of the class is about the PIC32, and the PIC32 is just another microprocessor chip. In this case, this is one of my favorite boards for the PIC32. This one is the UC32 board. You can see it's sort of in an Arduino kind of form factor with double headers like that. It works really well. It doesn't have a built-in debugger. You use a PIC32, for instance, or a PIC32 to attach to it there. But you can make it flash LEDs and things like that. Now, anyways, we're going to get talking about the PIC32s now. All right, so we're going to go through how the MPLAB X IDE works. We're going to take a look at how to set up a program, building up projects using the simulator, and doing some debugging. So a basic overview. You're going to see that it looks a lot like how we use the Atmega 328 board as well. All right, so it's important that you know that there's lots of material that you can resource on this. There's MPLAB X. We're up to version 5.35 at this point. XC32, the C compiler, is also available right now, and so you've got those available to you. Having access to the data sheets is also really important. We are using the PIC32 MX series. It's a relatively traditional or older version of the PIC32. It's well characterized, it's well known. There are newer versions of the PIC32 out there, the MZ, for instance. I think there's an MK edition, an MM edition as well. They're relatively the same. They're all based on the MIPS architecture, except for the PIC32C, which is an ARM architecture. All right, so moving on. New projects. Well, how do you set up a new project for the PIC32? It's a lot like all the other, the PIC16 and the Atmega 328 and the SAMDs as well in MPLAB X. Basically, you fire up MPLAB X, you do File, New Project, and you start with the Standalone project option. All right, and then you sort of follow the options from there. You want to choose the family, in this case the PIC32. Once you start typing in the family name, it will give you sort of options to work from. It'll prompt you for whether you want an MX, and then in our case we could choose, say, for instance, a 340 series, and then the numbers and letters that fall after that or follow after that have to do with the amount of memory and the chip configuration, like the shape of it, things like that. So anyway, it's important to know that those are there. If you want to just get started, you could use the 340. Another option would be one of the 250, so PIC32 MX 250, and then just choose one of those. We're going to do all of our examples in this semester with the PIC32 in simulation. You're not required to buy a lab kit for the PIC32. And then from there, you can choose XC32 C compiler. Now, in the past, only the C compiler was available, but now you can also choose C++. As of the last, I think, about a year or 2 years now, the C++ compiler actually works, which was a surprise for me. So if you want to try it out, you absolutely can, although we'll be giving our examples in terms of C. All right, from there, you can call your new project Hello World. I tend not to want to put spaces in there, so I wouldn't put a space. I'd remove that space. And then you set it as main project. It does that by default. Otherwise, you have to right-click on the project name and then select main project. And the reason you want to do this is because if you have multiple projects and it isn't selected as the main project, when you hit the compile button, it will likely compile a different project. And then that's all confusing and terrible, and don't do that. All right. So from there, the IDE MPLAB X is a really fantastic IDE. It's a little on the slow side and a little resource intensive, but it does work, and it's multi-platform. It works under Windows, Mac, and Linux, and it's free, which is fantastic. All right. When you're inside of MPLAB X and you've set up a project, it's important to keep tabs on the left-hand side, and you'll find the project sort of sub-window in there. All right. If it's not immediately visible, click on up above, window, and then open up the project option. From there, down below that project listing, you will see that there are details about your chip and so your project setup. It'll name what chip you're on. It'll say what version of the compiler you're at. Right now, we're not using 1.2. We're generally at 5.35 or above that, say 5.40, etc. All right, it'll tell you how much memory is being used, RAM and flash. So RAM is for like variables and flash is for like your program. So then you'll know basically what kind of resources are being used up by your, at least from a static perspective, that are used by your program on your chip, and you can choose different simulator tools like the PIC kit or the snap or just the simulator. At the bottom of the main MPLAB X window, you will find, like you did with the ATmega 328 projects, tabs for your logic analyzer and for your output, so it'll show you what's going on when you're compiling, etc. Up above at the top of the screen, you'll want to keep tabs on other views, or you'll want to include other views. For instance, the PIC memory views. Sometimes that name changes, but basically the memory views, you want to look at your program memory, your special function registers. The exact names change from one architecture to another, one version of the IDE to another, but basically what you're looking for are views of memory, debugging views, decompile or disassembly views, things like that. After that, the other thing that's important to point out is where you're going to be writing all your programs, and that's the editor window. And the editor window tends to be found, if this is the MPLAB X window, your project is over here, your main options are up there, the result of your compiling and some of your memory views are going to be down here. This right here, that's where your editor tends to reside. It's similar to what you would see in MATLAB and other sort of IDEs. Now, in order to start writing your program in here, you have to right-click on source files over here in your project view, right-click on it, and then do new, and then see source file or see main file. Generally, you want to choose the main file, and then you fill in your main from there. If you can't see it in here because your thing is so new, then choose other, and then find it from there. Some people like to have a white background, some people like to have a black background. Doesn't really matter, you can customize it up in preferences. Now, when you're creating your source file, while I did indicate here see source file, recently I found that generally speaking, you want to start with your main file right here. From there, generally as you're typing things out, you want to be making sure that you're saving things on a regular basis. Again, the symbol for saving does change over time. 1 diskette, 2 diskettes. If you can't figure it out, then type either in MATLAB, it'll be the command symbol and S, or control and S. All right, now, in the past, the very first thing that you would want to include in here would be a header file specifically for your chip. In more recent versions of MPLAB X, instead of writing that explicitly, you would write include xc.h. And this works for the PIC32, it works for, it'll work for the PIC16, it'll work for the ATmegas as well in the versions that I've tested so far. Now, in future releases of the XC compilers and for the MPLAB X, that might not be the case, but at least for the time being and for the past many years, it's been the case. Regardless of which you end up doing, what ends up happening is it ends up pointing to a specific header file for your specific chip, effectively your chip support package or your board support package, BSP or CSP. All right, and then inside of that, it's got all sorts of definitions for various registers and special functions that are inside of your processor. It's a very handy way to get started, much faster than actually was possible before. Now, from there, you want to generally add in a main function. And so the main function typically is int main void, and then down here at the bottom, you'll put a return and a number like 0, semicolon. But in between those, this is where you put lines of your C solution, your C programming solution, between the first curly brace and that last curly brace. Now, often what we want to do when we're getting started with any embedded processor is to make it light up an LED. That tells you that something is working, and you know, it's just a traditional sort of hello world approach to doing things. In order to do that, you have to configure the input-output pins, or at least one of them. And those input-output pins, when I'm talking about a chip, are the little metal things on the side of the chip. On this board right here, that chip right there is the processor, and all the little silver things along the edge, those are the pins. Some of them are input-output pins, some have other functions, but that's the thing that you want to be activating, those little metal things that are sticking out of the square or rectangular plastic box. They have the possibility for doing digital work as well as analog work, and many of them are connected internally, sometimes in very reconfigurable ways, to internal sort of semi-autonomous blocks that can do things like timing and interrupts and communications and analog processing, things like that. On the PIC32, just like on the ATmegas, you'll find that there are different ports. Port B, port G, port A, port C. It depends on your chip, it depends on the configuration. On the 340s, there's a port G and there's a port B. It's just different groups of functions that have been put together in a relatively convenient sort of approach. So there are different port groups with different functions. Port B, for example, contains a number of pins that can be configured as analog inputs for the ADC, the analog to digital converter. Port G can be used, or is typically used, for digital input and output. So depending on your chip, and you want to refer to the data sheet, you sometimes need to use port A instead of port B, or port G instead of port C. Look at your data sheet to figure out which one you want to use. Now, in the PIC32, just like in the PIC16, a little bit different than on the ATmegas, there's something called the TRIS registers. And these are referred, or they're also called the TRIState registers, and they are in charge of controlling the direction. That is a pin an input pin or an output pin? Does it read voltages from the outside world, or does it write or create voltages that go to the outside world? So we have TRIState pins, and those are the ways that you configure your individual pins. On the ATmegas, this would be the DDR register, the DDRB, so the data direction register port B. Same sort of thing for the PIC32, except we call them TRIState registers. All right. So let's see. From there, setting the bit to 1 in the TRIState register sets it to an input. Setting it to a 0 makes it an output. Every architecture is going to be different. Always refer to your data sheet. Now, just as we did in the ATmega series, the watch window is a fantastic way to examine and debug your processor as it's working. And so it's also available for you to examine things in the PIC32 when you're using the debugger mode. Now, when you're compiling your programs, you are writing up your program in C or C++. It takes each of these individual, if you've got multiple files, it will take each of these individual multiple files and combine them together, creating object files. And sometimes if you have external libraries, it will link those in. That this is a relatively complicated process, but luckily most of that is hidden from you within the resources of your IDE. Now, to sort of flex your computer architecture muscles, is often really good to have a board to do the work on. In cases where you don't have access to a hardware board, you can use the built-in simulator in MPLAB X. Now, it's not a 100% realistic simulator, but it's enough to get you started for the most part. It's good for doing resets and single stepping and running and halting your microprocessor. Now, oh, again, a little typo there. That should be xc.h, like that. So you can try out an example, okay? And so you'd want to set up your program again, int main void, like that, and then down here put a return 0, like that. All right, so if you've chosen the PIC32 MX340 series of chip, try to engage port B. So in order to make port B work, you have to, 1, set the TRIState register to 0, which will make all of the bits associated with port B outputs. From there, you want to engage the analog to digital configuration register that's available on port B, because it can be used as both digital and analog. Not both at the same time. You really want to have one or the other. On a particular pin, you set all the bits in that register to 1 by putting 32 bits to 1 using FFFF. Each of these is worth 8. Sorry, in this case, yeah, so each of these is going to engage multiple bits, okay? And then from here, so that's, sorry, this is 8 and that's 16. That's, yeah, that's right. Sorry, got myself confused there. So this will be 8 bits set to 1, another 8 bits set to 1, and then what you want to do here is set all of the bottom 8 bits to 1, which means each of them will be turned on to 3.3 volts if this is a 3.3 device, 3.3 volt device. Okay, so in this case, what you'll have are 8 pins, each set to output 3.3 volts. All right, so when you're dealing with these microprocessors, it's important to point out that going to the data sheet is often a super good idea. And what I've done here is brought out a screenshot from one of these data sheets. And you can see that, let me see now, the bottom 8 bits, so 8 bits, that would be bits 0 all the way to 7 are described there. Then bits 8 all the way up to 15 are described there. Then 16 all the way to 23. And then this is 24, bit 24 all the way to bit 32. Now, compare this to the Atmega 328, where each register only has really 8 bits. Each register in the PIC32 has 4 times that many bits. It becomes a lot more complicated to go through each of these, and you'll also notice that in this particular case right here, those top 16 bits aren't used. You only end up modifying 16 out of the 32 bits, and this is common for a lot of the 32-bit processors. A lot of the bits aren't used at all, and so in a lot of cases you're having to use less bits than are actually available in that architecture. Going up to 32 bits doesn't mean that you're necessarily using a lot more than you would in an 8-bit or 16-bit machine. All right, so whirlwind tour right here. Important to point out that we can, just like with the other chips, we can create new projects in MPLAB X. We can build projects just like we did with XC8, the 8-bit compiler. Just this time you're using the XC32 compiler. There are different ports that are available, and each of these ports has often different pins associated with it, and you have access to a simulator. So this is a quick overview of the PIC32 and what you'll be using in this part of the course.